Hi everyone, in this video we're going to look at the oxidation of alkenes, which is an important reaction because it's how alkene functional groups in drug molecules are metabolized. They are metabolized by an oxidation to form these epoxides. Now in this video we're going to show it via the reaction with a per-acid or per-carboxylic acid. In biological systems, this would obviously occur with a CYP enzyme, cytochrome P450 enzyme, which would carry out this oxidation. So let's have a look at what goes on. First thing that happens then is the pair of electrons from the carbon-carbon double bond is going to actually now form a bond with this oxygen here. What then happens is that the pair of electrons of this OO bond form a carbon-oxygen double bond. The consequence of that is that this carbon's now got too many bonds, and then the pair of electrons in this carbon-oxygen double bond form a bond with this hydrogen. That hydrogen then has too many bonds, and the pair of electrons in this OH bond form a bond with the other carbon, in effect. Now, this looks quite complex, so I'm going to number these arrows 1, 2, 3, and 4. So let's have a look at the products that we've got. So we've got this, I'm going to number these carbons, say 5 and 6. So carbon 5 has still got the CH3, nothing has changed there. And it's still got a hydrogen. Nothing's changed there. It's also broken the pi bond, but it's still got the sigma bond. So it's got the sigma bond, I'll just say there, to carbon 6. And we've still got a hydrogen and this CH3. Nothing has happened there. But what has happened is that curly arrow 1 has shown the pair of electrons in the pi bond forming a bond with this oxygen here. So let's draw that. But we can also see that curly arrow 4 has shown a pair of electrons from this OH bond has been used to form a bond with carbon 5. So basically this oxygen is now going to bond to carbon 5, same oxygen, and we get this epoxide. And that's the product. Now the net result of the other product would be this carboxylic acid here, and I'll just show you the consequence of that. Now curly arrow 2 shows the formation of this carbon-oxygen double bond. So you can see what's happened is that this bond's broken and this pair of electrons has been moved to form a double bond here. This pair of electrons now has been used to form a bond with this hydrogen. So this curly arrow 3, the consequence of curly arrow 3 is the formation of bond 3. So that's the oxidation of an alkene to form an epoxide. What usually happens to this epoxide then is that it's hydrolyzed, certainly in the metabolism of a drug which has got an alkene functional group. The first thing is they're oxidized to an epoxide, and then they are hydrolyzed in the presence. Obviously hydrolysis is with water. So let's have a look at the hydrolysis of this epoxide. This usually happens in the presence, certainly in the lab, of an acid or basic catalyst. In biological systems, this would be an enzyme. But what happens is that a water molecule is going to attack the epoxide, and it's, well, the first thing that's going to happen before that is that it's going to actually, an acid catalyst is going to be used to add to this oxygen, and that makes the carbons bonded to the oxygen more electrophilic. So we have this OH bond formed here. So the result of that curly arrow is that we've now got this, and again we need a plus charge because the oxygen has got 1, 2, 3 bonds. Now it's a hydrolysis, the water is going to come along, and the water comes along and attacks, and again it doesn't really matter which of these attacks because both carbons are kind of equivalent, but let's just say it's going to attack carbon 6. And once it attacks carbon 6, this carbon's got too many bonds and a bond's going to break. And it's going to break. And the pair of electrons are going to go back to this OH. So let's have a look. And again, I'll number this curly arrow 1, curly arrow 2. The consequence of this is, again, we'll start by looking at the carbon-carbon double bond. Sorry, the carbon-carbon single bond. Nothing has happened there. Still got a CH3 there. And we've got hydrogen there. Nothing's changed. Now, this bond has broken. Okay? So what this means now is we've got an OH here. And this lone pair. And this lone pair here has come from bond from curly arrow 2. So the pair of electrons from this bond has gone to the oxygen that's bonded to carbon 5, which is this here, 5 and 6. So that's what's happened. Let's see if we can figure that out. The bond between the oxygen and carbon 6 is broken, so there is no bond between this oxygen and carbon 6 now. This has been broke. A pair of electrons that were in this carbon-oxygen bond now are on this oxygen. What we can see is that the hydrogen bonded to carbon 6 has stayed as it is. The CH3 stayed as it is. But now we've got this OH2. This OH2, this water here, bonded to carbon 6, which is what we've got. The oxygen needs a plus charge because it's got 3 bonds. What then happens is that this hydrogen then is removed. And the net result then is we form a diol. So I'm just going to copy this. So the net result of this this bond breaking here is that this is lost and the pair of electrons go back. So I'll just tie that up. And there we get a diol. In this case we get butane 2,3 diol. So that's the oxidation of an alkene to form an epoxide, and then the mechanism for the acid catalyzed hydrolysis for the epoxide to form a diol.